Hello, in this particular session, let us discuss the characteristics of DC series motor. In the previous session, we have studied the characteristics of DC shunt motor. In that, we have seen three characteristics: the torque current, the speed current, and the speed torque characteristics. So, here also, in the similar way, we have to discuss three types of characteristics in case of DC series motor. So as already we know that by studying the characteristics, we will come to know the performance of motors or the behavior of motors at different loading conditions. How the motors behaves, how it responds with respect to the change in loads. That means sudden application of load, how it behaves when suddenly the load is removed under normal load conditions. Like this, we can analyze the performance characteristics of motors by observing the characteristics. So let us start with the torque current characteristics. So here you can observe the circuit diagram of DC series motor. So here, as already we know, the sum of the terms which is present in the circuit, that is the supply voltage which is given to the series motor. So as usual, the field winding, here you can observe RSE is the resistance of the series field winding. So in case of shunt motor, it was RSH representing the shunt field resistance. But here it is RSE, which indicates the resistance or the winding is placed in series with the motor. Therefore, it is called as DC series motor. In case of shunt motor, if you recall, the field winding was coming in parallel with armature circuit. But here, the field winding comes in series with the armature circuit. Therefore, it is called as DC series motor. So, if you observe the terms of current, that is IL represents the line current or load current, you can call. It comes from supply, you can observe. And ISC represents the current which is flowing through the series field winding. IA represents the current which is flowing through the armature conductors. RA is the resistance of the armature conductors and which is connected to a load. So here if you observe, we can call this as DC series motor because the field winding comes in series with the armature circuit. So here, for this type of motor, what happens if the load is varied? For that, for analyzing, let us go to the graph. So here in the graph, if you observe, in the y-axis it is represented by torque. In the x-axis you are having current, therefore it is called as torque current characteristics. So here if you observe the torque, already we have discussed about the torque in the last session. The torque is nothing but the axial force or the turning force or the twisting force which acts at the axis of the motor, at the axis of the machine. Because force is nothing but a linear motion, torque is nothing but axial motion. Only the difference is both the terms, if you observe force and torque, in both the terms there is a force, pressure is there, but in case of torque it acts axially. That is the difference you have to observe. So where the torque is developed, if you observe, the torque actually it is developed in the armature conductors. How the torque is developed, that one also we have discussed. Let us try to recall some of the things. So whatever the flux phi is the flux per pole which is present by the poles of the field magnets. You have to remember the construction diagram for this. If you remember the construction diagram, you are having stationary and rotating part. The stationary part contains the field magnets. On the field magnets, the field windings are placed. For that, when supply is given, and the supply is given to that, at that time it produces the flux. Whatever the flux which is produced by the field magnets, that is called as phi, represented as flux per pole. Later on, coming to the rotating part of the machine, there the armature conductors are placed. The conductors are placed on the outer slots, which is made on the periphery of the armature. For that, when the supply is given, the supply, if you observe circuit diagram here, the supply is given for both field part and the armature part. You can observe. Yes or no? Right. In the similar way, according to the principle of DC motors, whenever a current carrying conductor is placed in a magnetic field, the magnetic field actually it is created by the field magnets. The conductors, whenever the current flows through the armature conductors, according to the principle, it experiences a force. Each and every conductor which is placed in the armature experiences a force. All the forces of the conductor individually, collectively produces a torque. That torque, it is called as armature torque, which makes the motor rotates. Which makes the motor rotates. And the direction of force experienced is given by Fleming's left hand rule. Fleming's left hand rule. Okay. So based on this idea, let us move to the characteristics. The torque, we have understood what is meant by torque, and we know what is IA. IA is nothing but the current which is flowing through the armature part, you can observe. Okay. So here, for understanding the characteristics, let us try to establish a relation between the torque and the armature current. Let us try to establish a relation. So here basically we know that the armature torque is given by 0.1595 Z IA into P by A. That means whatever the torque which is produced in the armature, it depends on, according to the equation, if you observe, it depends on flux per pole, whatever the flux which is produced by the poles. It depends on the armature conductors Z. It depends on the current which is drawn by the armature conductors, and also depends on number of poles which is placed in the stationary part of the machine, and number of parallel paths. It is related to the windings. It is related to the windings. The armature conductors, actually it is connected in the form of lap winding or wave winding depending on the applications. So in that, the number of parallel paths you can consider. So here, from this particular equation 1, what we can tell, the armature torque, it depends on number of parameters, that is phi, Z, Ia, P, A, P by A. Okay. So if you observe this particular equation for the series motor, what are the constant parameters, what are the variable parameters with respect to load, if you consider? Because I am trying to apply the load right now. Let us apply the load, let us vary the load, and let us see how the torque is varied, For that, if you observe the phi and Ia, let us go to the equation 3. If you observe the phi and Ia, we can consider as a variable parameters. The other parameters such as armature conductor Z, the number of poles and parallel paths, it remains constant. It remains constant with respect to the load. Okay, what we can tell by the analysis of the DC circuit diagram of the DC series motor, we can write the equation 3 from equation 1. The torque which is developed at the armature is directly proportional to phi and Ia, because the phi and Ia will vary with respect to load. Because as the motor load is varied, the current Ia will vary, and whatever the flux which is produced by the field winding, that will also vary, because ISC will also vary. As Ia gets varies, ISC varies. Therefore, we can consider the torque is directly proportional to phi and Ia. Again, from the equation 3, we can write the equation 4 because the phi is replaced by Ia, because whatever the current which is flowing through the armature and the field winding both are same. If you observe the circuit diagram, I can tell Isc is equal to Ia, which is equal to IL. All comes in series. All comes in series. And therefore, finally, what I can tell by observing the from equation 1 and 3, I can write whatever the torque which is produced by the armature is directly proportional to square of the armature current. Square of the armature current. Okay. So, in the similar way, if you observe the equation 2, we will come across TSH and TL. We will come across TSH and TL. TSH is the torque which is developed at the shaft. TL is the torque which is lost due to the losses. Torque which is lost due to the losses. So, let us go to the graph. If we observe the graph, you can observe it is increasing parabolically. You can observe it is not linear. That means here what we can tell, let us analyze this thicker line first, that is the TA, and the dotted line if you observe that is TSH, that is a shaft torque. Here we are drawn a graph for armature torque and also for the shaft torque. So this is the armature torque is nothing but the torque at the armature or the gross torque what we can call total torque. The shaft torque is nothing but the torque which is available at the shaft for doing useful work. This is the torque which is available at the load for doing useful work. This is the torque, total torque, and some of the torque actually it is lost due to the losses. You can observe here this difference why we are getting this is the torque which is lost. TF is represented by TF. Here it is TL. Both are same. TL or TF represents the torque which is lost due to the stray losses, that is friction, windage, and iron losses, which is constant with respect to load. Which is constant with respect to the load. Those losses will not vary. So here, let us try to analyze TA first. Here we are having this graph. If you observe, we can divide into two parts. This dotted part you can observe. Up till this particular point, it is increasing parabolically. After that, it is increasing linearly. So here, the torque is directly proportional to square of a current. In this particular area, if you observe, the torque is directly proportional to Ia. There is a linear increase. So here, from 0, if you observe, as the load on the machine increases, as the load on the motor increases, what will happen? As the load increases, the current which is drawn from the supply increases, the current IL increases, therefore Isc increases. As Isc increases, Ia increases. As the load on the motor increases, the current drawn from the supply increases. As supply current increases, Isc in series increases. Ia also increases. As Ia increases from the equation 4, as Ia increases directly proportional to torque, therefore my torque also gets increased. My torque also gets increased. Therefore, which increases square of that. If you observe Ia if I take 2 amperes, then how much torque is increased? By how much the torque is increased? Which is 4 times. For 2 amperes rise in current, the torque is increased by 4 Newton meter, we can consider. If the armature current is increased by 4 amperes, you can observe 4 square. 4 square, that means 16. If armature current is 4 amperes, then what is the torque? It is 16 Newton meter. Like this, the torque increases square of the current. The torque increases square of a current. Okay. So like this, you will get a graph. Which increases square of that current. The torque increases square times of the current, we can consider. Up till this particular point. That means up till saturation of the core. Once the core gets saturates, after that the torque increases linearly. Torque increases linearly because we can neglect the term phi from this particular equation. That will become constant. That will become constant. Okay, until the saturation of the core. The saturation is nothing but, even though if you increase the mmf, even though you increase the mmf, the production of flux will become constant. The flux density will become constant. Okay, so up till this particular point, what I can call is the saturation point. Up till that, the torque of a series motor increases parabolically. Okay, after that particular point, the torque increases linearly because of saturation of the core. Therefore, it produces a high starting torque. If you observe that's characteristics of DC series motor, it produces a high starting torque because the torque is directly proportional to square of the current. Square of a current. So coming to graph TSH, if you observe TSH, here I will come across the term IA naught. IA naught. It is the no load current which is drawn by the armature when the load is zero. So it is drawing some amount of current if you observe. It is drawing some amount of current practically if you observe in order to maintain the losses. What we have talked about is stray losses, friction windage and iron losses, what we will call. Okay, IA naught represents the amount of current which is drawn by the armature at no load. Okay, again here also if you observe, as the load on the motor increases, the shaft torque increases in the same way as that of TA, that is parabolically it is increasing up to saturation. After saturation it is linear. It is linear. In the similar way you can analyze. But there is a difference because of this TL. Because of this TL. TL is constant. TL is constant. Therefore, as the load increases, IL increases. Because of that ISC and IA comes in series increases. As IA increases, the armature current which is directly proportional to torque gets increased. If you come to equation 2, as torque increases, TL is constant. Therefore, my TSH increases. TSH increases parabolically square times. Here also up till saturation. After saturation, it will become linear. It will become linear. Okay. So this is regarding the torque current characteristics of DC series motor which has got high starting torque. Which has got high starting torque. So next step, you can observe the speed current characteristics of DC series motor. So here the speed versus armature current you can observe. The speed, that is nothing but it is represented in RPM, revolutions per minute. So here again here also we have to establish the relationship in order to analyze a relationship between speed and armature current. We are not having direct relationship for this. So we have to establish by using with the help of some equation, that is EB. We know that 5Z NP by 60A, because already we have seen this particular equation, that is the back EMF equation, which depends on phi flux per pole, Z is the number of armature conductors, N is the, here you can observe the term what we require is N, the speed of armature in RPM, P is number of poles divided by 60A. So here if you observe, again the back EMF can be represented by EB is equal to V minus IA RA minus IA RSC minus ARD minus BCD. By putting KVL, if you observe this particular circuit diagram, if you apply KVL for this particular loop, I will get EB is equal to V minus IARA minus IARSC minus ERD minus BCD. ERD represents armature reaction drop, BCD represents brush contact drop. Already we have seen. In the shunt motor also, we have applied KVL and we have established this type of equation. So here, by comparing these two equations, equation 1 and equation 2, if you compare and equate the equation, you will get the third equation, that is the speed is directly proportional to V minus IARA minus IARSC divided by 5. So all the parameters here, if you observe, IA will vary with respect to load. We have considered that equation, and V is constant, the supply voltage. The flux will vary with respect to load. We have considered ARD, we have neglected, which is very small when compared to the load current. BCD also we have neglected, which is very small when compared to load. And Z, P and A, it is constant. 60 also constant. We can neglect the constants, and if you equate these two equations, you will get the speed is directly proportional to V minus IARA minus IARSC divided by 5. Okay. From this particular equation, if you go for equation 4, here also we can tell the speed is directly proportional to V minus IARA minus IARSC divided by IA. What he has taken, the flux phi is replaced by IA, because whatever the flux which is produced by field winding, it depends on ISC. ISC is equal to IA. Therefore, we can write, instead of flux, we can write which can be replaced by IA. Further, if you observe, you will get equation 5. Further, if you consider the values of RA and RSC is very small when compared to the load current, the RA and RSC is very small, which will be less than 1 or 2 ohms, point something. Okay, if you consider what I can neglect, we can neglect the numerator of the equation, we can neglect, and directly I can write the speed is inversely proportional to the current. So here if you observe the graph, as the load on the motor increased, as the load on the motor gets increased, automatically if you observe circuit diagram, the current drawn from the supply increases, that is IL increases, which increases series. ISC comes in series, ISC increases, therefore IA increases. As IA increases, if you observe, which is inversely proportional to speed, the speed decreases. Here you can observe, you will get a rectangular hyperbola. As the load on the motor is increased, the IA gets increases. The IA, which is inversely proportional to speed, therefore the speed decreases. Here the speed decreases inversely. So it is called as rectangular hyperbola because of two factors. One is the IA, the other one is a numerator part also. If you observe, we will come across a drop, IA RA drop and IA RSC drop. The speed of a DC series motor decreases because of two parameters. One is the IARA drop and IARSC drop, and the second one because of inversely proportional to the load current, inversely proportional to the armature current. Okay, so because of these two parts, the speed of the DC series motor decreases as the load increases. So here we can call DC series motor as a variable speed motor, because a wide range of variation of speed we will get, and it adjusts the speed as the load changes, as the load varies. So because of that, so here we can tell it is a variable speed motor. DC shunt motor, if you observe, it is a constant speed motor. The change in speed with respect to load was very small. The speed regulation was good. The change in speed from no load to full load, if you consider, it was very small. But here a wide range of speed you will get, a wide range. From no load it is maximum. At full load, if you observe, it is almost minimum. It is almost minimum. A wide range of speed we will get, and it adjusts with respect to load as the load varies. So we can call this speed, from the speed current characteristics, what we can call the DC series motor as a variable speed motor. A variable speed motor. So here what we have to remember, the speed of a DC motor decreases because of two parameters. One is directly proportional to V minus IARA minus IARSC, and inversely proportional to IA. Because of numerator part also the speed decreases, and denominator part also the speed decreases. But in the equation 5 it is very small, therefore we have neglected the numerator part because of RA and RSC. Because of the resistance RA and RSC is very small when compared to the load current, therefore we have neglected that. That's all. Okay, based on this idea we can analyze the speed torque characteristics. If you observe the graph, which is similar to that of speed current, because already we know that torque is directly proportional to the square of the armature current. Square of the armature current. So we will get a similar type of graph for speed torque characteristics. So here let us analyze this again with the help of the equations. With the help of equations. Equation 1, if you observe, the armature torque is directly proportional to square of a current. From the first characteristics I can write directly. The equation 4 of first characteristics we can write the torque is directly proportional to armature current. And from the second characteristics, that is the speed current characteristics, equation 5, I can write directly the speed is inversely proportional to armature current. So by comparing equation 1 and equation 2, what I can write, the speed is inversely proportional to square of the torque. The speed is inversely proportional to the square of the torque. Okay. So in the speed current characteristics, there also the speed was inversely proportional to armature current. Speed was inversely proportional to armature current. Here also the speed was inversely proportional to torque, but it is square of the torque. Okay, so here also if you observe, as the load on the motor increases, IL increases, which increases IA. As IA increases, what will happen? Torque increases, directly proportional. As torque increases, the torque is inversely proportional to the speed, therefore the speed of the motor gradually decreases. So what we can consider here, also a wide range of speed torque relationship we will get. If you observe at no load, if you observe, the speed is maximum. At full load, if you observe, the speed is minimum. Therefore by observing the speed torque characteristics also, you can observe that we can tell the motor is suitable for variable speed motor. At no load, but another point what you have to observe, at no load the speed of a motor is very high, hence it never be started at no load. Okay, because at no load, if you observe load is zero, means theoretically if you observe, current will become zero. At no load current will become zero. Current becomes zero means, which is inversely, the speed will become infinite. So always there should be some load, there should be some light load. So whenever you start a DC series motor, it should start with some light load. At no load it runs at very high speed, which is very dangerous, which will damage the motor mechanically, hence it should never be started without load. This one you have to remember. So overall, by observing the characteristics, if you recall the three characteristics of DC series motor, if you observe, what we can tell by observing the torque current characteristics of DC series motor, it has got high starting torque, what we can tell, high starting torque. And by observing the speed characteristics, that is a speed current or speed torque characteristics, the speed of a DC series motor will varies widely from no load to full load. You can call that one as a variable speed motor. So where the applications you can observe has been listed for various applications has been listed. You can go through that. That is, the first one is electric traction, the second one is electric locomotives, trolleys, cranes, hoists, conveyors, air compressors, vacuum cleaners, hair dryers, and sewing machines. So like this, if you observe, wherever high starting torque and large variation of speed is required, there we can go for a DC series motor. So based on these ideas, we can discuss some of the MCQs of DC series motor. The first one, if you observe, the running speed of a DC series motor is basically determined by, the one is field excitation, second one is load, third one is armature resistance, fourth one is none of the above. The running speed, the speed, if you observe the speed current characteristics or speed torque characteristics of motor, you can observe the speed, it depends on Ia, inversely proportional to Ia. Ia, it depends on load. How Ia varies? It when the load is varied. When the load is varied, Ia gets varied. Therefore, what we can tell, the answer for equation 1 or for the MCQ first is load, we can consider the option B. The option B. Because as the load on the motor varies, then automatically the speed of the motor gets varied. The second one, a DC series motor will overspeed when, that is, when the load is increased, when the field is opened, when the armature circuit is opened, when the load is removed. So already we know, we have discussed, when the load is zero, then automatically the speed of a motor is very high, which runs at higher speed, which damages the motor mechanically, we have seen. Therefore, a DC series motor will overspeed when the load is removed, So we have seen that DC series motor, whenever it starts the DC series motor, they we have to apply at least light load. Some load should be there. Then only we should start the DC series motor. Okay. The third question, if you observe, DC series motors are used in those applications where dash is required. You can go for high starting torque. Option A. Already we have seen from the torque current characteristics of DC series motor, the torque is directly proportional to square of the armature current. Therefore, the DC series motor are used in those applications where high starting torque is required from the characteristics, that is torque current characteristics, Therefore, we can go for option A. The fourth one, for the same rating, dash motor has the highest starting torque. For the same rating, dash motor has highest starting torque. That is the series motor. Where the torque directly proportional to square of the armature current. When the fifth one, when the load is removed, the motor that will run at highest speed is dash motor. When the load is removed, when the load is zero, if you observe, when the load is removed means when the load is zero. At that time, the motor that will run at highest speed, that is a DC series motor, you can observe it runs at dangerously high speed, that one you have seen. Therefore, we can go for option D. Which motor should not be started at no load? Here also, it is DC series motor we can go for. DC series motor should never be started at no load. Some load has to be applied, because we have seen from the speed current characteristics, it will run at very high speed, which will damage the motor, which will come out of the foundation. Therefore, it should be started at some load. Therefore, for option, we can go for this particular question, you can go for option D. The armature torque of DC series motor is proportional to the armature torque is directly proportional to Is square, we have seen. So here what he has given: field flux, armature current, field flux and armature current, and field current. If you observe, you can go for option C, that is field flux and armature current, because from the torque, if you go back and if you observe the equation of, if you see the equation, that is torque equation, the armature torque is directly proportional to flux and also Ia. Later on, we have replaced flux by Ia. Okay, from the equation 3, what we can tell, the armature torque of a DC series motor is directly proportional to field flux and also armature current. Okay, we can go for option C. Which of the following motor has a poorest speed regulation? The speed regulation, if you observe, what is regulation? The change in speed from no load to full load. If it is very small, then I can tell it is very small, then I can tell it has got a best speed regulation. But here if you observe, the speed regulation is very high, the change in speed is very large. Therefore, what we can tell, the series motor, DC series motor has got the poorest speed regulation, because of wide range of speed variation we will get by the speed current characteristics. You can observe. Buses, trains, trolleys, hoists, cranes requires high starting torque. Therefore, make use of DC series motor. You can go for option C. Yeah, that one we have seen from the applications. Whichever the applications require high starting torque, those applications you can go for DC series motor. The last one, if you observe, the DC series motor are used. The DC series motors are used where load is constant, where load changes frequently, where constant speed is required, none of the above. Here you can go for none of the above. Where the DC series motor is used, we have seen from torque current characteristics, wherever high starting torque is required, wherever wide range of speed variation is required. Therefore, here we can go for none of the above. None of the above. The equation, the question number 11, if you observe, dash motor never used belt connected load. Never used belt connected load, because whenever the belt is disconnected, whenever the belt fails, at that time suddenly the load will become zero. So in the series motor you have seen, whenever the load becomes zero, then automatically it will run at very high speed, it will damage the motor. That one you have seen. Therefore, a DC series motor never use belt connected load, because whenever the belt fails, it will run at very dangerously high speed. Therefore, you can go for option D. Option D. The demand for a large increase in torque of a DC series motor is met by, the demand for large increase in torque of a DC series motor is met by, you can observe, large decrease in speed. Large decrease in speed. That one you can observe by observing the speed torque characteristics of motor. Speed torque characteristics, if you observe, when I will get large torque at the DC series motor, whenever the speed decreases, you can observe, whenever the speed decreases, at that time I will get large amount of torque. So for the question number 12, if you observe, the answer is, the demand for a large increase in torque of a DC series motor is met by a large decrease in speed. A large decrease in speed. Therefore, we can go for option B. Whenever the speed decreases, whenever it comes to a minimum value from maximum, then a large amount of torque is achieved in the DC series motor. Therefore, you can go for option B. So, in this particular session, we have discussed the three different types of characteristics of DC series motor. By observing the characteristics, we can conclude the DC series motor is used wherever high starting torque is required, and a wide range of speed variations can be achieved by the DC series motor, and the DC series motor should not be started at no load. If we start, then it will damage the motor. It will run at very high speed. Okay, thank you.